Hi, and welcome back to my Physics Online video lecture supplement series. In today's video, I wanted to discuss fluid dynamics. Specifically, I'm going to ultimately be talking about Bernoulli's principle in fluid flow, although I wanted to start with a little question before the lecture to help motivate the lecture, which is, what happens if you hold a piece of paper loosely from one end and then blow over it? And more importantly, why does that happen? This is something you can do fairly easily at home. You will notice basically if you hold a single piece of paper without blowing over it, that typically it kind of folds so that it's vertically oriented, save for the part that's in your hand and the little part that's bending to make the main body orient vertically. If you blow very rapidly over the end of it, then what tends to happen is the paper sort of rises up a little bit. And we're going to look at the reason behind that in this lecture, among other things. We're going to look at basically two types of flow ultimately, which is streamline or laminar flow, in which every particle is going to be moving sort of through a parallel path, and basically every particle will move along the same path as any other particle which passes through a given point. So this picture sort of shows what laminar flow might look like. Every particle in this particular line of smoke follows the same line. Every particle in this line of smoke follows the same line. There's no mixing of the two lines. The other type is irregular or turbulent flow, and in this case you don't get very well defined paths. This would be like if the smoke was intermixing between each of these streamlines. And the one that we're going to look at today is laminar flow. And this one is usually associated with low velocity fluids, fluids in which all direction changes are gradual, and not very high velocity per se, no large sudden changes of direction. So again, if you look at this picture, you have flow that does have directional change as the air passes over the car, but there's no sharp directional changes. If this windshield were more upright, if the car were a little less aerodynamic, then you'd get some turbulence in the area where the wind is hitting the upright windshield and sort of mixing. So I've kind of described one minor use of fluid dynamics, but there's a number of other interesting applications for fluid dynamics. For one, there's the question of what happens to blood vessels when you get plaque buildup. There's also the question of what happens when you turn on your water faucet and you watch the water falling out of the end of it. You may notice that it narrows a little bit as it falls. So the question is, why does that happen? A more practical application than that is in making an airplane fly or in steering a ship in the water, etc. And last but not least, you may have had the experience of walking into usually a public restroom and there's a very foul odor coming from the drain in the floor. It's not because somebody has sort of done their business where they shouldn't, but it is usually because there is still some seepage of sewage into the bathroom through the drain. And the question is, how is it that you remove that stench without tearing the drain apart? So let's talk a little bit about an ideal fluid, because this is the type of fluid that's going to lend itself most easily to laminar flow. So a truly ideal fluid is going to be non-viscous, which means that there are no internal friction forces between adjacent layers in the fluid. That also basically means that the layers of the fluid are not shearing past each other. The fluid will be non-turbulent. Of course, that is exactly the definition of it being laminar. Laminar and turbulent are the two types of flow that you can get. That basically means that you're going to tend to have zero angular velocity about the center of the fluid, and there's not going to be much in the way of eddy currents. The fluid should be incompressible. That means density is remaining constant. It basically is a reasonable approximation even for water, as a simple calculation of how much water compresses under the depths of the ocean would show. And last but not least, you need steady motion. So velocity and pressure remain constant at each point. That also means the density is remaining constant, which would be sort of part of the incompressibility, but it's also a part of having the motion be steady. And these things are all constant as functions of time. Unfortunately, real fluids tend to be more complicated than ideal fluids, but very often we can approximate a real fluid as an ideal fluid and get some ideas of how it is going to act. Sometimes you can approximate a real thing as the ideal thing and then make a very small tweak or perturbation to your model to get a more accurate picture of what the real thing is doing, in this case a fluid. So the first principle that we should know about fluid flow rate is what's called the continuity theorem. And basically the way that continuity works is this. Let's define a new term called flow rate, which we're going to define by a capital Q. And that will be volume per unit time. You could also think of it as mass per unit time, since for an incompressible fluid, the volume times the density gives you the mass. But I'm going to use volume per unit time because geometrically that's easier to deal with. That's going to look like, therefore, the cross-sectional area times the length over which that cross-section remains constant divided by time. And since distance over time is an average velocity, this means that the volume flow rate can be given by the cross-sectional area times the speed at which the fluid is flowing through that cross-section. Now, what this volume flow rate is going to do for us is relatively simple. Mass tends to be conserved for a given fluid. Conservation of mass is a conservation law that's generally obeyed in classical physics. It may be violated by things like special relativity or nuclear reactions, this kind of thing. But in classical physics, mass is conserved. And fluid usually is acting in the classical regime, which means that the amount of fluid that goes into a volume or section of container has to equal the amount of fluid which comes out of that volume. In other words, fluid is not created or destroyed as it flows through some section of a container or a pipe or what have you. And what this means is that the mass flow rate, and since it's a non-compressible fluid, therefore the volume flow rate is constant. So that means that Q in is equal to Q out, or cross-sectional area 1 times the speed through that cross-section must equal cross-sectional area 2 times the speed of that cross-section. And this is what's called the equation of fluid continuity. So let's return to that question I posed earlier about the stream of water coming out the end of your faucet. Well, you notice in this picture, this nice snapshot, that the stream is thicker up top near where the water first comes out of the faucet than it is down low. So the stream is basically narrowing as it falls. And the reason for that is because of this continuity equation. Basically, if a vessel widens, then the speed of the fluid needs to decrease, and if a vessel narrows, then the fluid is going to increase. Fluid speed will increase accordingly. And so that means that this volume and this volume are equal. So you can see that in this diagram basically, because if this volume and this volume are equal for a given amount of time, then a bit of fluid, a particle of the fluid, must go from here to here in this part of the container, and then when it narrows, that same particle must get from here to here in the same amount of time in order for these two volumes to actually be equal. And so that tells you how much more the speed must be for the fluid in this part of the container than in this part of the container. So returning to this faucet, you don't really have a container, but the fluid is still sort of contained in the stream, if you will. And it's largest at top because the water is just now beginning to fall, and that means that it has relatively low speed. And so as the water starts falling, that means it has to start speeding up, and so therefore the stream must narrow in order to make up for the fact that the water is going faster. So let's do a simple example of this. Suppose that you have water which is in this pipe, and it's initially flowing at 1 liter per second, and then the pipe narrows. We want to know how fast the water will be traveling after the narrowing. So this one has a continuity equation which says A1V1 equals A2V2. And what we want to know is how fast after the narrowing. That would be V2. So this right here is equivalent to Q1. And this right here is equivalent to the cross-sectional area before. So this would be A1. This is the cross-sectional after A2. So recall that Q1 is equivalent to A1V1, and Q2 is equivalent to A2V2. Is it going to be equal to Q1? So what all of this tells us is basically that V2 should be equal to Q1 over A2. So in fact, we don't necessarily need to use both of these areas and this flow rate. So therefore, V2 should be 1.00 liters per second divided by 0.0400 square meters. Well, what is 1.00 liters per second in a more useful unit? Well, we need to convert this into cubic meters. So convert to meters cubed. So 1 liter is equal to 0.001 cubic meters. So this right here is 0.001 meters cubed per second. We're dividing that by just 0.04 meters squared. So that means that the speed of the fluid is about 0.025 meters per second, or if you'd rather, it's 2.5 centimeters per second. So that's the speed of a particle of this fluid in this part of the container. So in 1 second, this particle would move from here to here, and this distance right here would be 2.5 centimeters in 1 second. So delta T equals 1 second. All right, so let's do another short example just for completeness sake. Specifically, we'll do a short example involving water falling out of a faucet. All right, so we have the initial cross-sectional area. We'll call this A1. we have the initial speed. So this is V1. What we're looking for is the volume flow rate. So this would be Q. And then we're looking for how large is the stream. So either we can find area 2, or if we want R2, when it hits 0.3 meters below. So let's find the Q first, because that's going to be relatively easy, since Q is the speed times the cross-sectional area, which would be 0.250 meters per second times 8.00 centimeters squared. We got to convert this centimeters squared into meters squared. So that would be 1.00 square meters per 10,000 square centimeters. So therefore, the volume flow rate should be given by about 2.00 times 10 to the minus 4 meters cubed per second. So this is our volume flow rate. This is incidentally equivalent to 0.200 liters per second, if you want that. Second part of the problem is how large is the stream just before it hits the sink 0.3 meters below. So what we got to do to determine that is we got to figure out what the final speed is. And we can use something like the fact that this is going under a constant acceleration. So v final squared minus v initial squared should be 2 times that acceleration times the distance that it falls. So this right here is equivalent to delta y. V initial, of course, is this v1. A is given by the gravitational acceleration. So the final speed should be 2 times g times delta y plus the initial speed squared, all under a square root. So final speed is square root of 2 times 9.8 meters per second squared times 0.300 meters plus 0.25 meters per second squared. So that gives us a final speed about 2.44 meters per second. So V final, we'll put it's 2.4377 for what that's worth, meters per second. Okay, well, we've already found what the volume flow rate is. It's this, and Q should be equal to V times A. So the final cross-sectional area should be whatever this flow rate is, Q, divided by V2. And so that is 2.00 times 10 to the minus 4 meters cubed per second divided by 2.44 meters per second. So that gives us an area of about a little over 0.8 times 10 to the minus 4, or in other words, 8.20 times 10 to the minus 5 meters squared. So this is the area. This could be converted into square centimeters. So this right here is also equivalent to 8.2 times 10 to the minus 1 centimeters squared. So that can also be used to try and determine what the radius is, if we wanted that, of the stream as it's hitting the sink. It's a radius of about half a centimeter. So R2 is about 0.511 centimeters for what that's worth. And that, of course, you get by dividing this by pi and then taking a square root, because the area is pi times r squared. So we're assuming a circular cross-section. The second principle that I wanted to introduce in this lecture is called Bernoulli's Principle. And to get to Bernoulli's Principle, we can apply a few physical rules that we've already encountered. The first one is basically how much work is done on the fluid. And the answer is that you have some fluid which is being pushed along by the back pressure from the fluid behind it. And work in general is Fx delta x, or F dot r. This becomes pressure times volume. So the pressure times the volume gives you the work done by the fluid on fluid that's after it. So this fluid is working on the section of fluid after it, this fluid works on the section after it, etc. The second principle, of course, is one we've already seen in this lecture, that is the continuity equation. So if the tube widens or narrows, then this equation is obeyed. There's also the possibility that fluid might change height in moving through this tube. Those changes in height are primarily going to affect pressure, but with that said, pressure is ultimately also going to drop when the fluid speeds up. So let's put all those things together. We have conservation of energy, which says that work plus kinetic energy plus potential energy must be constant, provided that there's no external work done on the system, provided that the system is isolated. And in terms of a fluid, you can get this by using pressure times volume, that's work, plus 1/2 times the mass of a particle of the fluid times the speed of that particle squared, plus the mass of the particle times the gravitational acceleration times the height. So here is your work, here's your kinetic energy, here's your potential energy. Recall, by the way, that this is a laminar flow. This means that we don't have to worry about angular momentum, angular speed, and angular kinetic energy. So that's why there is no omega squared terms in here. And the way that Bernoulli's principle works is that you take every term in this equation and you divide by the volume. And so when you do that, this term right here is PV, just becomes P for pressure. This is 1/2 times the mass times the speed squared. Well, mass over volume is density, so you end up with 1/2 times rho times the speed squared. And then again, mass over volume gives you the density times g times h. Again, this is rho for density. And so Bernoulli's equation says that pressure plus 1/2 times the fluid density times the speed of the fluid squared, plus the density times the free fall acceleration times the height must remain constant. So it's basically a conservation of energy equation. So let's look at an example which makes use of Bernoulli's principle. All right, so you have water which is flowing through a tube which is narrowing from one area to another by a factor of 4 in area. So this tells us that A1 over A2 is equal to 4.00. And what we're going to do basically is we're first going to use continuity to get the final speed of the water. So we'll use the continuity equation to get V2. Then we use Bernoulli's principle to get the final pressure, P2. So this right here is P1, this right here is V1, this is that ratio A2 over A1. Final speed, would be V2, final pressure would be P2, and the other thing that we may want is that this is water, and so that means that the density is 1.00 times 10 to the 3 kilogram per meter cubed. And that's just because that's the density of water. So let's apply these principles and get the speed and get the pressure. So continuity basically says that V1 times A1 is equal to V2 times A2. So by implication, V2 should be this ratio A1 over A2 times V1. So that is going to be 4.00 times 8.00 meters per second. So that means that V2 must be 32.0 meters per second. So now we have the speed at which the water is traveling through the tube. Now, this means we can apply Bernoulli's principle, which says that the initial pressure plus half of the density times the initial speed squared plus the density times the free fall acceleration times the initial height should be the final pressure plus half of the density times the final speed squared plus the free fall acceleration times the density times the final height. So let's look at our diagram again. And you can see in this diagram that on average the water height is unchanged in going from the first part to the second part. Yeah, some water up here is moving to a lower height, some water down here is moving to a higher height. On average, the height is staying the same as this change is occurring. So on average, that means that we can get rid of those height terms. All right, so that means that this term and this term go away. We're solving for P2, so we can rewrite the equation as P2 equals P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared. Or in other words, P2 is 1,500,000 pascals. That's the same as a Newton per meter squared, plus half of 1,000 kilogram per meter cubed times the difference in these speeds squared. So the difference in speeds squared would be 8.00 meters per second squared minus 32.0 meters per second squared. Okay, so P2 should therefore be given by, would be 1,500,000 pascals, and ultimately these two subtracted, this subtracted from this is going to give 960. So divide that by 2 and you've got 480, multiply by 1,000, you've got 480,000, and it's negative, so minus 480,000. And the units balance to pascals because this is meters squared per second squared. Kilogram is a kilogram times a meter per second squared is a Newton. So you end up with 1 meter left over from that Newton to cancel this out, and you've got newtons per meter squared. So our units balance, and what you end up with is that P2 is 1,020,000 pascals, or 1,020 kilopascals. What I want to do now is make use of a fluid flow simulation which is put together by the folks at Colorado, at the PHET group in the University of Colorado. And in this simulation, what we basically have is a enclosed container going from one pipe to another, through which there flows a fluid. And what I can do here is I can change the width of the tube, which basically means change the cross-sectional area, and I can change the height of the tube. And I can adjust the flow rate, but I'm not going to do that for now. I can look at the speed, I can look at the pressure, and I can look at the flux, which is basically flow rate per unit area. The ones that I'm going to actually pay attention to here are going to be the speed and the pressure, and we can use a ruler if we want to measure how high one tube is above the other, or even how high the bottom of the tube is from the top. So this tube is basically 2 meters thick, and already what I can do is stick this pressure gauge in and see if the pressure varies at all from top to bottom. Before I do that, you should ask yourself, is this something that you would expect to see happen? Okay, let's go ahead and measure the pressure at the top. And it is a little over 110 kilopascals. And now we're going to go ahead and measure the pressure at the bottom. So it was 110 kilopascals at the top. So at the bottom, what would you expect the pressure to be? Well, looks like it's about 129 and a half if you get to the very bottom. A little under 129 and a half. So we gain roughly 19 and a half kilopascals of pressure from top to bottom here. So the question is that something that you should expect to have happen? So we basically had delta H equal 2.0 meters, and we basically had delta P equal something like 19.5 kilopascals. Recall that we could either use fluid statics or we could use the part from Bernoullis Principle, which states that the density of the fluid times the free fall acceleration times the change in height should give us the change in pressure. Now, we can look at what the fluid density is, and in fact we can actually set the fluid density if we want. It's set for water, which is 1,000 kilograms per cubic meter. So we basically can write here that rho is equal to 1,000 kilogram per meter cubed. So the expected change in pressure here should be 1,000 kilograms per meter cubed times 9.80 meters per second squared times a change in height of 2.0 meters. And so this gives us an expected pressure change of 19,600 newtons per meter squared, which is the same thing as 19.6 kilopascals. And that is indeed the pressure change that we observed in the simulation. This is in fact the pressure difference that we actually observe. See, here's 109.966 kilopascals, and then if I am really careful in putting this to the bottom, 129.454. We're pretty close to 19.6 kilopascals difference here. It's maybe within the margin of error for my ability to set this pressure gauge. And so we see that this principle that we see in fluid statics and that is utilized by Bernoulli's principle is upheld in this simple case. So now let's do something a little more complex. One thing that we can do that's more complex is we can adjust the height at which the pipes are going to sit. And so here all I've done is just moved the pipe from, let us say, a total height difference of 2 meters. So this pipe is now sitting about 2 meters below this pipe. So let's go ahead and measure the speed of the water everywhere in here. If you look at the red dots, you notice that they're more or less moving at the same speed no matter where they are in the water. The red dots represent sort of a single molecule of water, if you want, or a single cohort of water that's moving together. And no matter where I drag this speedometer to, or velocity meter if you want to call it that, since it's showing a direction as well as a magnitude, I get the same speed. It's 1.6 meters per second. It's true at the top, it's true at the bottom, it's true down here where this pipe is, it's true up here where this pipe is. So the speed is not changing a whole lot. What about the pressure? How does the pressure change? Well, before I go ahead and put the pressure gauge on here, let's ask again, what do we expect to have happen? Well, at the same location within the tube, we should be about 2 meters difference in height. So if I look at the middle of the tube and the middle of the tube, I should be about 2 meters difference in height. And so that should be about 19.6 kilopascals difference in pressure. And bottom of tube to top of this tube is probably going to be pretty close to 4 meters, and so that should be pretty close to 36.2 kilopascals pressure difference. So let's go ahead and test that out. I'm going to just put this at the top of the tube here, and it seems to measure around 19.3, there's 19.25, let's say. So we'll call it 19.2 kilopascals. And let's go to the top of the container here. Now it should be less when I put it here. Right now it's measuring atmosphere. When I put it right here, it should be less than the 19.2 that I measured here. And in fact, see here we had 119.2. Over here, I'm going to expect, therefore, something like 100 pascals when I put it at the very top. And sure enough, we get pretty close. It's not perfect. It's not exactly 19.4 because you'll notice that the way that this little tubing curves, we're not really making it to the top of this tube. In fact, if I use the ruler to measure this distance, 1, 2, let's say maybe 3 of these, which represents 0.6 meters worth, so that should be a difference of about 5 to 6 kilopascals. And sure enough, if we actually were to measure here, 104.2 over here was 100 and I guess we can get to 118.8 or whatever. And if we're measuring actually in this tube, probably the very top of the tube, call it 120.1 if we're being really careful. Hard to be careful because it's hard to see exactly where the top of the tube is supposed to be, whether we should count it as here, whether we should count it here. But if we count it from here, 121, and we say that's equivalent to this point here, 104, that's 17 kilopascals difference. That's pretty reasonable within our order, within our margin of error. All right, so what else can we change in this? Well, we can change the thickness of the tube at various points. So what I'm going to do for my last little trick is I'm going to narrow the tube over here. I'm going to widen it as much as I can over here. Which seems to be difficult to do with the actual tube. There we go. So let's go ahead and make it as wide as we possibly can here. And narrow as we can up here. So we'll kind of narrow it a bit. Maybe narrow it not as much here. So I want it to sort of taper. So there we go. And that's about as close as I can get to a nice gradual tapering. So now let's go ahead and measure the speed. First of all, you can look here and see that this part appears to be moving slower than this part. So we expect the speed to change. And in fact, if I put it just barely in, 0.2 meters per second here, and if I put it over here, it's almost 6 meters per second. Let's see what the difference in size is, by the way. So this tube is more than 4, more than 5 meters across. So we'll try to find where it's 5 meters across. Maybe about here. It's 5 meters across. And here the speed is about 0.3 meters per second. So the flow rate, well, we can use the flux meter to cheat if we want to get the flow rate. The flow rate is 5,000 liters per second. So let's see if the 0.3 meters per second times this radius of 5 meters gets us that flow rate. Let's go ahead and check this volume flow rate. So the volume flow rate should be Q equals V times A. Now V was given as 0.3 meters per second. A is basically a circular cross section, so I actually measured the diameter. D equals 5 meters. So area should be pi times D over 2 squared. So the volume flow rate should be 0.3 meters per second times pi times 5½ meters squared. And so if you plug all that into a calculator, let's see, 0.3 times pi times 25 divided by 4 gives us actually 5.89. So let's call that 6 meters cubed per second, which is the same as 6,000 liters per second. So we're a little off from what the program is showing here. Then again, I don't have necessarily a very good accurate measurement of the speed. Like my level of precision is not necessarily perfect here. My level of precision in making this measurement is not exactly perfect. In fact, I'm probably over measuring the height of the tube and probably should actually be measuring somewhere in here. And so within our margin of error, we really are getting about 5,000 liters per second. Okay, so let's go ahead and move the speedometer over to the far end again, where the speed is now 5.9 meters per second. 6, right where it's entering the tube, I guess. So let's see if that holds true to our calculation. Let's pull up our ruler. Right where it's entering the tube. Again, this is kind of a hard one to actually get a measure on. I guess it's about a meter across, give or take. Now we have a volume flow rate, Q equals V times pi times D over 2 quantity squared. And that now is more like 6 meters per second times pi times, let's say, 1 meter over 2 quantity squared. So that gives us something more like, let's see, 6 times pi times 1/2 squared would be a quarter, 4.71. So Q equals 4.71 meters cubed per second. And again, this realistically is more like 5 because we don't really have that many digits of certainty. And so we can write Q as 5 meters cubed per second, which is 5,000 liters per second. So our continuity equation is working out here. Okay, what about the pressure? Well, let's go ahead and try to measure the pressure. Might be actually easier to do by resetting everything here and remeasuring, just because it's going to be a little tough to get pressure at this location versus this location. So let's do it like this. I'm going to stick this meter stick so that the grass is at the 1 meter mark, and I'm just going to take the pressure there. And it appears to be 90, let's call it 92.7 at this part here. And so now I'm going to measure that same pressure over here, kind of having to estimate that this is the same level. And so the same pressure over here is 110.3, let's say. So let's see what the actual pressure difference should be. So according to Bernoullis Principle, since I measured it at the same height above, or as the case may be below the ground, H1 equals H2, and so we can write P1 plus 1/2 times the density times V1 squared is P2 plus 1/2 times the density times the second speed squared. So let's go ahead and use the pressure that we just got, that second pressure. Again, that's 110, we'll just call it 110 kilopascals. So we have 110,000 pascals plus 1/2 times 1,000 kilogram per meter cubed times this difference in speeds, so 0.3 meters per second squared minus 6 meters per second squared, and that should give us pressure 2. Alright, so let's see, 0.3 squared minus 6 squared should give us about 36 still. So this whole thing is going to be, let's see, divide that by 2, still at basically minus 18,000. And so that means that P2 should be about 110,000 kilopascals minus about 18,000 kilopascals, or 110,000 pascals minus about 18,000 pascals. So that should be about 92,000 pascals, or about 92 kilopascals, which is fairly close to what we got in doing this measurement. So let's stick this guy over here, and 92.6 versus 110.2. Within our margin of error, that's pretty good. So it looks like Bernoulli's principle works out very nicely on this simulation, which is what I would basically expect from the folks who put these together. They're pretty good. So those of you watching this who want to play around some more with it, you can go check out these guys' website, Colorado PHET, and then pull up this simulation if you'd like and play around with it a little more. I wanted to look at an application of Bernoulli's principle to blood flow through, basically through our blood vessels. Plaque starts building up inside of your blood vessel, and that basically narrows a section of the blood vessel. So this section is more narrow. That means that the speed of the blood through this section has to increase in order for the continuity equation to be satisfied. And with the speed increasing, that also means that the pressure will decrease in this section. And when the pressure decreases, that's a very bad thing. It can lead to what's called vascular flutter. Basically, the blood vessel is not very rigid, and so it's held inflated largely because of the fact that we have high enough blood pressure to keep it inflated. So if you lose blood pressure in some area of it, thanks to, for example, this plaque, this high-speed blood flow, and therefore nearly zero pressure here, then the artery should kind of collapse in this area. And when the artery collapses, then no blood makes it through this part, and so you get a temporary interruption of blood flow, and that's the vascular flutter. So what happens to the blood over here when that occurs? Well, you start building up pressure here, and that basically will cause the artery to reopen, but it also causes a second problem. As the blood pressure here builds up, the walls tend to weaken, and this tends to stretch out. It inflates kind of like almost like a balloon, but not, I don't want you to think of this thing like expanding to 7 times its volume or something, but it does stretch out a little bit. And when it stretches out a little bit, that increases the pressure a little bit, which means that it's going to stretch out a little more, which means that you're going to get a little more pressure. And eventually, you get enough pressure that it can exceed the strength of the blood vessel, and your blood vessel bursts. Okay, I want to mention another interesting example of Bernoulli's principle, really 2 applications, which is in flying an airplane and in sailing a boat. Airplane wings and sailboat sails both use Bernoulli's principle. The airplane wing does it by basically being shaped in such a way that you get a different speed of the air above than below. And so they try to make it so that the speed of the air passing over the wing is faster than the speed of the air passing under the wing. And when they do that, it means that the pressure from the air under the wing has to be larger than the pressure from the air over the wing. So that gives us a net force on the bottom side of the wing upward, not just a buoyant force, but an additional force from the difference in pressures due to the flow rates of the air. And so that creates lift, which allows the airplane to fly. A similar process is used in using a sailboat to head into the wind. You can see here that the boat is basically pointed more or less directly into the wind. The sail is angled in such a way that you get a lot of very high-speed air passing over the front of the sail and very little high-speed air, basically lower-speed air, on the back. That means that your pressure on the back of the sail is going to be greater than the pressure of the front of the sail. And so that gives you a net force from the wind, force being pressure times area, and so this pressure times this area minus this pressure times basically the same area gives you a net force of the wind in this direction, and then the rudder dragging in the water gives you a net force in a different direction, such that when you add these 2 net forces, you get a total net force that is basically into the wind, and hence the sailboat can sail directly into the wind. So what I have in this diagram is a typical, if somewhat simplified, setup of the drain system that might be found in your home. It's true actually of office buildings, basically anywhere that needs to have a drain system. And usually what happens is that everything that has water in it, be it a sink, be it a toilet, be it the dishwasher, etc., is drained into a common sewer pipe, which then goes out to the sewer. The toilets, the bathtub, the sink, etc. And so what would happen here if we just left this as is? If it was just a simple tube, and when sewage or wastewater or whatever entered it, okay, it flows to the sewer and then nothing. Well, what would happen is that then this would be dry, empty, and you'd get fumes from the sewer, which would sort of go back through the sewer pipe, and they'd try to come into the house. And this vent thing, that's not going to be a problem. I'll talk about what that's for on the next slide. The dishwasher largely isn't going to be a problem because there's usually some reserve water sort of in the basin of it. So nothing's going to get in through there. Toilet, same thing. You have water in the toilet bowl. The real problem is stuff like bathtubs, the sink. If you're in a public building, usually a public restroom might have a little drain in the middle of the floor. All of those would be potential avenues for this horrible odor to get into the house. And so in order to prevent that, we put in an additional little device in the sink or under the toilet or under the drain. And it's this U-shaped device like this. It's a trap! And this item is called a trap. Basically, how it works is that water creates a little plug here underneath your sink, underneath your bathtub, underneath the drain in the public restroom. And so this plug prevents any of the sewage fumes from seeping in through the sink, etc. They basically hit this boundary and then they can't continue through. However, we also need the second device, this vent, in order to prevent this trap from being sort of sprung prematurely. And by that, what I mean is you run the dishwasher, and what happens is that the pressure drops over here on the sewer pipe side because you've got moving water from the dishwasher moving down to the sewage. So you've got this moving fluid. Therefore, the pressure drops. Therefore, the water that's in this trap sort of gets pushed through the trap and into this area by the outward pressure here. And that's absent this vent. You just have a tube leading into the sewer. So then when the dishwasher ceases, there'd no longer be water in this trap, and so the odor from the sewer could then seep through and get up through the sink. Well, by putting the vent here, what happens is you run the dishwasher, that causes the pressure to drop here, and instead of pulling the water out, you draw more air in from the outside to keep this water in the trap, and therefore when the dishwasher ceases, the trap is still in place. And therefore, you don't get any foul smells into your house. All right, I wanted to close by working through an example that involves blood flow in the human body. And I'm going to start by trying to estimate how many capillaries there are. So this starts out fairly straightforwardly. We use the continuity equation, which says basically that V1A1 equals V2A2. Now, we're going to use this as radius of a capillary. This will be radius of the aorta. This will label as speed in the capillary, and this will label as speed in the aorta. So in those terms, this basically becomes number of capillaries times speed in a capillary times area of a typical capillary is going to be equal to speed of the aorta times area of the aorta. And these areas, an area of either is basically pi r squared. So this basically says N is equal to VA over VC, AA over AC. And so that becomes VA over VC times, the pi's cancel, you're basically left with radius of the aorta over radius of a capillary quantity squared. So the number basically looks like 28.0 centimeters per second divided by 550 microns per second is the same as 550 times 10 to the minus 4 centimeters per second, since there's 10 to the minus 4 microns in a centimeter. Then with the radii, we had 1.25 centimeter, and we're dividing that by 4.00 times 10 to the minus 4 centimeters, and then we're squaring that. So if you plug all those in, what you end up with is about 4.97 times 10 to the 9. So about 5 billion capillaries. 4.97 times 10 to the 9 capillaries. Okay, there's a follow-up question that could go to this, which is, what is the typical blood pressure in one of these capillaries? Now, I'll grant that this is not going to be a perfect answer because the height within your body is also changing. But if we assume that the height is effectively averaged to be about the same as the height of your heart, what would this make the blood pressure in a typical capillary? Well, P1, really we're going to find the change in blood pressure from your heart to your capillary, because we don't have the blood pressure at your heart. But P1 plus 1/2 rho G H1 plus 1/2 rho V1 squared is P2 plus 1/2 rho G H2 plus 1/2 rho V2 squared. And again, we're going to kind of make the simple estimate that the height is more or less averaged to be the same. So we're not factoring height into this. So change in blood pressure should be 1/2 times the density times the change in the blood speed from capillary to aorta. So that would be P2 minus P1 should be 1/2 of V1 squared minus V2 squared times the density. Blood has a typical density of about maybe 1,060 kilograms per cubic meter. So rho for blood, we'll say 1,060 kilogram per cubic meter. A little higher than water, basically. So this means that the expected pressure change should be 1/2 times 1,060 kilogram per meter cubed times, we'd probably better put the everything into meters per second. So basically 0.28 meters per second squared minus 5.50 times 10 to the minus 4 meters per second squared. So this gives us a change in blood pressure of about 41.5 pascals. So 41.6 pascals. So that is your expected change in blood pressure then from heart to basically end of one of your capillaries before returning through the vein. And of course you need that higher pressure because there's nothing at the point where the blood is returning to the heart to actually pump that return, save maybe in the soles of your feet, where maybe you could, in some animals and maybe in people, get a little bit of pumping action as you walk. By and large, it's going to be due to this difference in pressure. So I hope that you've enjoyed today's lecture on fluid dynamics. There's more to be discussed in further fluid dynamics. I really didn't get much into the difference between laminar and turbulent flow and what causes turbulence and what causes viscosity in a liquid, and basically how viscosity can take a liquid from being laminar to turbulent, and about the Reynolds number, which is a measure of about when you go from laminar to turbulent flow. What velocity do you have to hit before you start getting turbulence in a given fluid? But that's all that I have for today's lecture. So I hope you enjoyed today's lecture, and thanks for watching.